area between curves. Area between curves. All right. So I'll start with this. There's a formula for this, and you all are going to develop the formula for us. So I'm going to do, hey, I don't know, y equals x. I'll just plot the 1 on the x-axis. Y equals x is a straight line, right? Cool. What I want you to do is go back to Calc 1. Think about Calc 1. I was wondering if you could give me the area underneath y equals x and think of some mathematical way to do that. And I'm going to give you another problem to work. We're going to find the area under, and I think I'll just go out to 1 again to keep this simple, our first example. Let's get the area under y equals x squared. Y equals x squared is a parabola, right? And I just want the area underneath the curve from 0 to 1. So I'll make another wall. So the area underneath y equals x from 0 to 1, the area underneath the 0 to 1 from y equals x squared. And you don't have to tell me the answers to these, but I was wondering if you could tell me the method. Going back from Calc 1, it was something you learned in Calculus 1, the method to find the area between that function and the x-axis. What do you do? I heard it. Take the integral. She goes, take the integral. So I'm going to take an integral of this. I'll go from, what's the x values? 0 to 1. I'll put the function x, and then we'll just write dx, right? So when you agree that would find the area under here? All right, you get the area. That gives this area. Well, what about this one? Very similar. Let me shade it in. What would be the area under this? Well, that'd be the integral from 0 to 1, dx, right? Well, what goes here? X squared. Two separate problems, but you know what to do, right? And I mean, of course, we can evaluate this. But you and I are now like, no, we're in Calc 2 now, we're going to get the area between curves. So the problem at hand for us, everyone, in section 6.1 is this. Can you find the area between here, y equals x, and here, y equals x squared? Hey, they do meet at x equals 1, don't they? So I'm going to shade this. And you're going to create a formula for the class. Watch out, the students in this class will develop the formula for this. How do we find the area between two curves, or two functions? You know?
The top minus the bottom.
He goes the top minus the bottom.
For the integral.
He's looking at this and saying, if you put this inside of here, you had to get the difference. He's saying, just take the difference of these two, right? So we'll just subtract. It's like, I can get these two answers and subtract them. That's the math formula. So he said, the math formula for us, I'll put it right here, is we'll just go the integral, some function f of x minus some other function g of x, if I'm getting the area between the curves. Here, I'll put dx. I like how you said top and the word bottom. He said top, you can think that way. Because which one, everyone, if you look at this picture, which one's really on top? And you look at it this way, the y equals x. And which one's on the bottom? Y equals x squared. He's saying if you just subtract these, you'll get the difference between them, and you'll get the area of those curves. So that's what I'd like us to do. Can we just do this math right here? I'll erase these two, and we'll set up our problem like this. We got it. Take the difference of these two. Get all this out of the way. We can do this in one integral, right? Sure, I could have taken that answer and subtracted, but we're saying go from 0 to 1. Who's the top, though? X or x squared? Good. Good. You can put a parentheses around this. And just, let's see what we get. What's the antiderivative of x? X squared over 2. What's the antiderivative of x cubed? I mean x squared.
X cubed.
X cubed over 3. And we'll go from 0 to 1, plug 1 in these two values. Then we'll plug 0 in the two values, we'll subtract them. Now let's see what we get. Okay, I get a half minus a third. 0 minus 0, I like zeros. The only thing is I need a common denominator, huh? Look, if this annoys you, pull out the calculator and calculate that. But I know that's what, 3/6 minus 2/6? What's 3, 6 minus 2, 6? What's the area? 1, 6. It's the exact area in that curve. Thank you for developing the math formula for the course, right? There's our first formula for our course, area between curves, top minus bottom. F of x minus g of x, single integral. I think the only challenge will be finding these a and b values. When they get us two expressions, we got to know where they intersect, right? So we got to use those old algebra skills of how do I find where two equations meet each other, or two functions meet each other. Is that okay with that? Excellent. All right. So let's try one. We're like, hey, can we go a little bit harder than this? So this is, I'm picking a problem. It's like one of the practice problems I was mentioning. And I made this one up. How about this? Here's one of the functions. F of x equals 4x minus x squared. My other function is function f of x equals x squared minus 8x. If you're curious, if you want to know which problem this is like from the textbook, it's like number 13 from section 6.1 if you're curious. It's like number 13. All right. The question. Find the area between these two curves. Find the area between the curves. Now, right now, everyone, unless we make a picture, I don't know who's the top and who's the bottom, right? And we don't want to be guessing. So we'll make a, not be a perfect picture, but a decent picture. Isn't that like an up U? Good. Negative x squared. Wouldn't that be like this? So now I'm going to make a picture in a sentence, but it looks like we've got like a what? Something like this, and it looks like you got something like this. Who do you think's the top? Just your guess by just knowing so far.
X squared minus x.
This one. Now negative in front of an x squared makes the graph's going to look like this. That looks like that's going to be the top one, right? It appears you're going to be the top, you're going to be the bottom. Now I just did a what? A freehand drawing right here, but it looks like what's going on. The problem is when we set up that integral, we got to find these important limits of integration. Where do these two things meet? True? Now that was a sloppy picture. If you wanted a better picture, it's like, let's see. If I factor that, when x intercepts, I just have to set y equals 0, right? If you want a decent sketch, you can make it with a calculator. If I wanted to sketch that a little bit better, let's just find these x-intercepts. I backed out an x. It looks like it meets the x-axis at 0, 1, 2, 3, and then over at 4. So this graph's doing something like this. Right? How about this one? Oh, you want to factor that just to see where it meets the x-axis? X and what? 8? Okay, so I better extend this a little bit further so you can see it. I'm just making a decent picture. 5, 6, 7, 8, and in here, this thing's gonna do what? Down here and then come back up like this, maybe? It's not a perfect sketch, but what area are we looking for? All that. When we're looking for this entire area, we've got a math formula for it. The only problem is, we've got to find out where they meet. So first, I'm going to set up the problem. To find the area between the curves, draw an arrow. It will be the integral of top minus bottom. Who's the top? 4x minus x squared, right? That's this one. Who's the bottom? The only challenge, you all know this, daggone it, where do they meet, right? Now when I already have a typo on purpose, I have an error up on the board. I didn't want you to make this during an exam. Or in your practice. I didn't even put these down, I've already screwed it up. Anybody spot it? Oh, look, the hands are up, they're like, they know. What do I need right there? Parentheses. Where some of you distribute automatically, you got to subtract the quantity of that other expression. So very good seeing that. Now these two things, we need these numbers. I'll just put question marks for now. What are these two values? How do you in math find where two functions meet each other. What do you do? That's right. And we can do the substitution method, where we can take one and substitute in the other, vice versa. He said 7 equal each other. So when I got 4x minus x squared, that's, and isn't f of x just a y? So if you can think of this, all right, you're like y, and this f of x is another what? Y. He's saying because they're both y's, set them equal to each other. Go off to the side of your paper, then we'll come back to this, we'll find these two numbers. So, does it show over here? Hey, all right, so I'm going to do it right here. Where does 4x minus x squared be equal to x squared minus 8x? I'm doing this to find where they meet. So I'm just going to put it on top of this. Meet, question mark. Where do these two things meet each other? And how do I solve something like this? When I'm going to add x squared on both sides. I'll subtract 4x on both sides. 0 equals 2x squared minus 12x. Can you help me solve that? We don't need the quadratic formula. Can we factor that? What can I factor out of that? X, factor out an x. And anything else? A 2. And when I factored out 2x, I'm left with x minus, so what are the 2x values where they meet? X equals 0, and x equals 6. Somebody might have guessed it from the picture though, huh? Right? But I didn't do the best picture. And look, this was not drawn to scale because this would have been right at what? Right around the 6 mark. Right at x equals 6. Let me get this out of the way. Right there, the meeting. Hey, that's something you can also explore with your calculators, true? But you'll always be able to find algebraically where these two functions meet each other. Great job. So let's go ahead and solve this. Should I start doing antiderivatives or should I collect like terms? That's up to you. I'm going to collect like terms first, inside here. So let's see, what's 4x minus x squared plus 8x. What do you get? I just thought I'd collect the like terms first. You get 12x minus what?
2x squared.
2x squared, all right, 12x minus 2x squared. So far so good? What's that antiderivative? 12x squared over 2 is 6x squared? Antiderivative of this? Minus 2x cubed over 3? Oh, I love zeros. All I gotta do is plug that 6 in there and subtract them, right? And you know this. Doesn't the answer have to be positive? All right, what's 6 times 6 squared? That's 6 times a 6 times another 6.
216.
216. Okay, thank you. What's 2 times 6 cubed over 3? So that would be 2 times 216 over 3. I think 3 goes into 216, doesn't it? 72 times? All right. Oh, by the way, I can do it, but when I plug zeros in there, what do you get? 0 minus 0, good. What's 216 subtract? That's 72 times 2. What's that, 144? You can use your calculator too to see that. All right, what's 216 minus 144? 72. There's your area. We got it. There's our area. It is positive. We knew it had to be positive. Let's see if you have any questions on that problem. Yes?
Why do you have to positive?
Why is it always positive?
Yeah.
Super question. As long as we set it up properly, as the top minus the bottom, it will always do that difference and give you a positive answer. So isn't that cool? Now, this has happened before. What if a student did all this work properly, found these numbers, but accidentally did the bottom minus the top? What do you think would come out as their answer? Negative 72. So if that happened during a test, what do I recommend? You're like, okay, you could just recognize, you go, whoops, I did this, I'm seeing it now, and draw a picture, maybe say, here, I should have had this on top and bottom. You don't have to erase it. What you want?
Formula can be like 1 minus the other if I take the absolute value.
Brilliant, everyone. Hear what you just said? she's creating a side formula. She goes, you know what, here's another formula. I'll put it here, but this is Sean, right? Sean's formula says, you can think of it like this. If you mess it up, now look where I'm putting the bars down. If you accidentally mess up the top and the bottom, right? She's saying just as long as you do that, you're still going to get the mathematically correct answer. You see that? That's called Sean's theorem.
But that's not like logically correct? Like,
True.
Oh, okay.
Isn't that cool? Because it will happen where I'll go, oh man, I had these switched.
Yeah.
I meant to do it and I still wrote it wrong. And you're like, well, by Sean's theorem, I'm just going to take the S right there. Just make sure, hey, be careful. Don't put the bars here. That's something totally different. Right? You put the bars inside here, that'd be different. She's saying like the absolute value of the final answer. Hey, Sean's theorem. Good. I like that. Hey, you can think that same way, everyone, when we get to 6.2. What she was just talking about. I want you to think that way if you accidentally make an error and go, wait a minute, can I still do something like that? What you're just doing. That would be in case I messed up the top minus the bottom. Okay, great. So we're like, man, I think we've got this section conquered. Well, there's a couple more scenarios. Everyone, what are we going to do in this scenario? This happens a lot. Not everything's a function. Not everything's a function. And so, y is a function of x. Passes the vertical line test, right? So you might get something like, oh, I don't know, a graph like this, right? You might get some graph that looks just like this. And, X and the Y axis.
You might want to grab a seat or something. Isn't it? Yeah.
So in this case, is this a function?
I'll turn the camera off for a second, okay?
Hey, Connor, Dan and Clarence, just check with me, I'll give you the documents. Hey, we're good? All right. And we're almost done with 6-1, except for, what about scenarios like this? Think top minus bottom. Isn't something weird happening? Like I just made this express, this is not going to pass the function test. By the way, this is the equation like x equals y squared. And, you know, it's kind of bizarre with the top minus bottom. You're like, the top is the, you follow me? And so we're like, all right, we're going to have to look at those type of scenarios in a second. Oh, you know what to do.
The bright mind's lost.
Oh, great, I'm coming to you. All right, so let me give you a picture. He's onto something. So we're talking about like, what do you do in situations like this, like x equals y squared, and as you're noticing, you're like, well, that's the top, that's the bottom, and gosh, I'm going to get the same kind of thing going on, it could get me confusing. So let me pick a problem. Hold up. Hey, when I made up one. Oh, this is number 12 from the textbook. So this is number 12 from section 6.1. I thought it was a good one. This is what they wrote. 4x plus y squared equals 12. And y equals x. And we've got to find the area between these two. Go find the area that's between those two curves. Although y equals x is just a straight line, isn't it? Okay. I'll get this out of the way. And we might write another formula over here on the board. Because this worked fine when these are two what? Functions of x that pass the vertical line test and stuff. So let's make a decent drawing of this one. That's easy. That's just a straight line, everyone, right? You know what these graphs look like? This 4x plus y squared equals 12. If you solve for x, let's just see what we get. We get 12 what? Minus y squared, what will x equal? What's 12 divided 4? 3 minus y squared all over a 4, right? Well, these things open up like this when it's x equals y squared, but isn't that x equal to a negative y squared? So how do you think this thing will open up? It's going to look like this. I just want to point out, x equals y squared, just so it doesn't confuse you, if you haven't sketched these before. It opens up something like this, x equals a y squared. This is x equal to 3 minus a y squared. So this will look like this, correct? When I put the drawing here. Now, I'm going to sketch this. Let's make a pretty decent drawing here. Because pictures are important. Make a picture. Can you help me find this x-intercept? I know this thing's just going to open up like this curve. Because it's an x equal to a negative y squared. You might go up here. How do you find x-intercepts? What do you set equal to 0? Yeah, for an x-intercept, all we do is we set y equal to 0. I think you'll find it easier here. Would you set y equal to 0 and solve for x? What do you get? Is that negative 3? You know, for an x-intercept? So x equals what? There's 3 minus y squared. Cool. So in this case, I went 4x plus y squared equals 12. We're saying this is negative x squared plus 3. And in this case, if y equals 0, is x equal to just 3? I just want to make sure. Is that what I agree? Is that a point on that curve? 3 comma 0? Let me put it. It's the vertex, isn't it? But which way is this thing opening up? Like that. All right, let's do it. Doesn't have to be perfect. That's one of the curves. That's that curve, right? Shifted over 3, and then it what? Cool. But I wanted to do this. What I did was I just found the x-intercept. I thought it was the easy point to find to get this thing going. And then y equals 0. It hits this value of x equal to 3. That's not that bad, right? And it opens up like this. Hey, if it was an x equal to a y squared, it would look like this, wouldn't it? Cool. Now, we all know what that is. That's just a what? Straight line. All right, just make a straight line. I'm not drawing a scale, but look at this image carefully. That top minus bottom thing's not going to work here so great. I mean, you could still do it. It'd be much harder, though. So what we're going to do is prepare another equation up here. And you're onto it. So I'm going to go to you in a second. And when we look at this, look carefully at this image. From here to here, the top is the y equals x, and the bottom is the curve, right? What happens after that? Right up to that point right there. Who's the top? The curve, and who's the bottom? The curve. Do you follow me? Things switched in the middle wouldn't give us the correct answer. So, you had a great solution to this. He says, don't think top minus bottom. Think, what was it again? Say it again.
Right minus left.
Right minus left. He's saying when you get a scenario like this, where it's like, oh, the top was here, then it stopped being the top at this point, then this was the top. He says, think right minus left. So right now, can you do one of two things? Either think of this as right minus left and twist your head like me, but I don't want you to get a neck cramp. Or take your piece of paper and do what? Twist that. And do you see what he means? He says he's creating the same formula, except you're looking at it this way. I'm turning my head because I can't turn this green board, but you might just turn the paper to see that. So your equation was put everything in terms of y, but do right minus what? Hey, that'll work. But I mean, the only thing is, we got to make sure we write all these variables in terms of what letter? Y. Brilliant. And when you notice the entire top, over here, from here to here, this is the right. From here to here is the left. It's always right over left. You see that? This is always the right side over the left side if you're looking at it that way. Cool. Now, which one of these is the right? I know you know. Which one's on the right side? You can write, and if you want to put a subscript of r for right, you can. X of r for the right side curve is the, what is it? 3 minus y squared over 4. Now, who's the left side curve? X equal to what? Here's x sub l. Here's the left side, right? X sub l is just equal to what letter? And I'll set up our problem. Right, minus, left. Who's on the right? 3 minus y squared over 4. And who's on the left? Y. Now we're going to look carefully. What letters do I have up here? They're all in terms of y, so I'm not putting a dx, I'm putting a dy. And we'll do this for scenarios like this. Yeah, you could have done top minus bottom, but that would have been a pain, right? We had to break it up into 2 expressions. Now, I'm challenged. Thank you for coming up with that. Very good. I'm challenged now with this. How do you get these numbers again? How do we find where they meet?
Set them equal to each other.
Set them equal to each other.
One's
Somebody
already
might
given,
say,
isn't
well, another way of saying that is substitute, right? So how about let's take this, substitute into this, and let's find, you gotta be y values, right? You got a sense, there's one of the y values, right there. The other y value is way down here. Well, we gotta find it. What are these 2 y values? So everyone, let's just go off to the side here. And we're gonna say, I had 4x plus y squared equals 12. I'm gonna get out of the way. I'm going to substitute for the letter x. What letter? Y. This is called the substitution method. All I'm doing, people say set one equal to each other. What I'm doing is setting that letter y in place of what the x was. It's the substitution method. Now when I got to factor that, so I'm going to subtract the 12 on this side. Y squared plus 4y minus 12 equals 0. Does anybody do 2 numbers to factor this? Multiply to negative 12, add up to 4. That was good. Positive 6 and negative 2. So what are the 2 y values for my limits of integration? Negative 6 is one of the y's, and the other y? You got it. 2, and this will give us the area. Ta-da! Will be a positive answer too. So far so good? Yeah? And we'll solve this. We'll solve this, everyone, but this will give us the area between those 2 extremes. So hey, I think you're discovering something. I guess the picture is really important, right? Yeah, we really want to get a sense of what they have there in terms of these drawings. What's the integral of 3? Okay, what? What's the integral of minus y squared over 4? Y squared over 12, and y squared over 2. So when I'm just going to write this out, 3 times what? 2 minus 2 cubed over 12 minus 2 squared over 2 minus, now I got to plug into what? The negative 6. What's 3 times? You've got to be very careful with these negatives, don't you? Minus negative 6 cubed over 12 minus negative 6 squared over 2. So be careful with doing that arithmetic in there. Some of you may use the Math 9 function off your calculators. Do you know what I'm talking about? Check this, very good. Known as a definite integral function on your TI-83s and 84s. You want to check that definite integral. But if you're going to put that on your calculator, just be careful. All this, subtract this quantity, we know the answer is going to come out positive. I did it earlier, everyone, if you want to crunch out all the math. Would you, just to check, you should get 64 thirds for your answer. Or 21.3 with a line over it, right? But right there, when you get to this step, you're just either doing the math mentally, on paper, using the technology to support you in finding these values. Just be careful with all those negatives, that's all I ask. And another thing, I saw the head nods like this. I asked students, hey, if you wanted to check to see what this answer is, you can use the Math 9 function off those TI-83s and 84s that does definite integral calculations. If you're curious, like, can you show me how to do that? Oh, it'd take less than a minute for me to show you. Just wait till the end of class, so you gotta check it. Sound good? And again, if I had this, backwards, I would have got negative 64 over 3. You can just put the bars in, right? Hey, cool. How many copies? Oh, we can all done copy. We don't have to solve the next one, but can we at least set it up? I think there's only one other scenario we gotta talk about. I think you know what to do. So it's either top minus bottom or right minus left, right? Always works. It's amazing how this concept of right minus left can be very helpful in Calc 3 too. I didn't want you to think about that. It's a really important concept where you look. Depends on the picture. How I'm gonna look at this problem. I can erase, are you sure?
Yeah.
You sure? I'm looking around. I want to erase before someone else. Yeah? Okay. Good? Nice. Hey, one more thing from 6-1. I mean, I'm talking about, let's just look at two simple trig expressions. Yes, sir?
On a test, do we have to show the antiderivative, like of us working all the way out, or can we just use the calculator?
So if you did this right here, after that step, you wouldn't have to show me any other math. You can use any method you want to come up with that final answer. Did that make sense?
Yeah.
So like you said it, but you would have to show the antiderivative. Good question. Show the antiderivative. Show your limits that you're plugging in there. Show that, hey, I'm going to plug these in like this.
Okay.
But then to get this, you might be like, well, I'm going to use the technology to facilitate the arithmetic.
Okay.
And I understand that, because that calculator has that tool. Great question. Great question. Yeah, at least show that antiderivative. Thank you. I'm going to have one more scenario. What if here you got something like these two curves? We're very familiar with these two, right? I'm not going to go very far with them, too. Let's just go out to pi over 2. What does the sine curve do? Doesn't it do this? Doesn't it get up to what, a 1? What's the cosine curve do? And then it does this, right? So and what if I said, find the area between those bounded regions here, between sine and cosine, find the area between these two, on this region right here, from 0 all the way to what? Look at the image carefully. And let me know. I'm going to write something on the board and I'm going to go to you first, okay? Because you came up with the last one. I'm looking at this. I see sine and cosine. We've been told this is the formula. So I want to know, will this work? Can I just go like this? Look, 0 to pi over 2. The top, sine. The bottom cosine. Will that work? Something's wrong, isn't it? Do you notice? From here to here, who's the top? That's right. The top is the cosine. Starting here, who's the top? Sine. So how can we approach this problem? What do you think?
Split it in half.
All right, so you're saying you want to integral, we got to find this number here, right? Right now, you just want to call it A? We don't know it yet, just call it A. Do an integral from 0 to A. Who's the top? Cosine of x. Minus the sine of x, dx. Then add that solution to, what's this? A to the pi over 2. Who is the top? The sine of x. And who is the bottom? What we're saying is, we know how to approach this problem. You don't have to finish all this work here, right? And then we'll talk about that A dot. The key was the 7. But I know right now you're like, what the heck's that A? The key is we just knew how to approach this problem. Even Sean's awesome theorem from before wouldn't work here because of how they switched over in the middle. Right? So we had to handle it carefully and find out who was the top, who was the bottom, when did they stop, and then who became the top and who became the bottom, right? But do you all agree, we evaluate this, we're going to get the right answer? Cool. Now, does anybody know a common angle or sine of this angle is the same as the cosine of angle? It's between 0 and pi over 4. Does anybody know what that angle is?
Pi over 4.
This is 90 degrees. I heard it. What was it? 45 degrees, pi over 4. So if you're curious, what is that angle? I didn't want to make it too hard on you. You know, like, you sit there, should I use a calculator on that? It's that pi over 4. The cosine of pi over 4 is 1 over square root of 2. What's the sine of pi over 4? 1 over square root of 2. It's that 45 degrees. So I'm going to put that right here. That's where they met. And so we'll just put these A values, we didn't know this before, and we'll put that in there. There you go. And you don't have to work this out. I know you could. I know you could, but you don't have to. You know, keep going. I know you can do that. What's the integral of cosine? What's the integral of sine, right? So you don't have to finish this all out. Oh, by the way, this, good idea by the author. He put this as an example. So he put this on page 425. If you're curious, you want to look at this out of the textbook. There's an image of this, finding this area between them. Hey, I apologize. I should shade too. I didn't have this shade. Let me shade it. That was top minus bottom. And that's top minus bottom. This was cosine of x. This was sine of x. And then the top became the what? Sine of x. And who became the bottom? Cosine of x. They both intersected at 0 equal to pi over 2. But page 425, if you want to look at, all the writing on that, you can do this. And if it helps everyone with doing integrals of sines and cosines, go that way, you get integrals, right? So what's the integral of a cosine? Sine. What's the integral of a negative sine? Students write this on the papers all the time during the test. Just to help them determine the what? The antiderivatives. So it's just something I'll probably write from time to time, because sometimes you just don't want to mix up, is the integral of cosine sine, or is it negative sine? Is the integral of sine cosine, or is it negative cosine, right? You just want to be careful with that. So I'll write this from time to time. And these are just negatives. Alright? You know how to set this up, brilliant. That's every scenario. We saw the what? When it flips over at one point, sometimes it's good to do right minus left, depending on the image, or top minus bottom, or you know how to find area between curves. Cool. Right. You got it. You got it. Can I erase? Hey, in the notes, put 6.2. 6.2. This starts. The other just writes volumes. I can erase these formulas. Okay. So erase this. Put a 2 here. And we're just going to spend the rest of the class on volumes. We're going to take some region and think about revolving that solid around a certain x-axis or y-axis. One of the axes. So we'll start with this. How about just y equals x? We always start with a simple example. And when y equals x, just this time, let's go out from 0 to 2. You see that area right there? From 0 to 2. We're going to find the volume of the solid. That's an area. We're going to find the volume of the solid. All right? Such that this area is revolved around the x-axis to form that solid. So if this area right here gets revolved around the x-axis, like this, we're going to find the volume of that solid. Well, there's the area, y equals x. Take the area underneath y equals x, and this x-axis from 0 to 2, and let's find the volume of a solid. With a solid created, it's created by such that the area underneath this expression right here gets revolved around which axis? The x-axis. They have to specify which axis they're talking about, right? So, can we, in our notes, I know it's going three-dimensional now, right? Could we make a rough sketch of what that would look like, even though it's on a two-dimensional plane? If this thing's getting revolved around, and this would get revolved around, make a loop, and this would get revolved around, and this would get revolved around, and what would this end up looking like? A cone. Did you hear that? Someone said cone. Wouldn't this look like a cone? We're like here. Just keep revolving this entire region all the way around the x-axis. It's making a three-dimensional solid, but it turns into a what? A cone. Well, the why is how do we approach this? It's very, very similar to doing area. Except then what we're gonna do is, we're gonna take the summation. Alright? Integrals find summation, right? That elongated S for summation. We're gonna sum a bunch of areas of disks. So this is the disk method. See all these disks in here? Think of it as a Riemann sum. But what am I gonna sum up? An infinite amount of area of disks. The only thing is, someone's gotta help me out. What's the formula for the area of a disk? I'm talking about a circle. Pi r squared, and here's our formula. We're just gonna, you wanna put the pi out here? Put the pi out in front of that integral, and let's just call this what? Radius squared, and we can call it function squared. Will that work? That's if it gets revolved around which axis though, we should put that in the notes. I've got a pi, I got an integral, f of x. We can put the a and b, you know what the a and b values are, what is it, 0 to what? I went out to 2, right? 0 to 2, the function squared, because isn't the function the radius? Isn't that the radius of this? Look. Isn't that the radius of this expression? Cool. But I'll put this in notes. If this gets revolved around which axis? RAV for revolve. You could say about or around, about the x-axis. This method. Cool. Now, what if you got something like this? You know, when I'm talking about the region right here. 0 to 2, 0 to 2. This is still y equals x. Isn't y equal to x the same as x equals y? But what if I wanted this revolved around the y-axis? We need a formula for that. We need a formula for that. So you find the volume of the solid generated by revolving this area about the y-axis, right? And what would the image look like? Whoop, 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 whoop. It'd be three-dimensional, right? Wouldn't it look like this? So what's the formula? I bet you know. First of all, it's not going to be dx, it'll be what? dy. Function in terms of y. Pi radius squared, that's our radius. Pi r squared, that's our radius. And you get the two values for y, the limits of y. Pretty cool? Alright, question.
How would you get the limits for the
Great question. Now in this problem it was given to you. I know it was presented to you, 0 to 2. 0 to 2. So both of these you would just go 0 to 2 and you'd find your answers. But I know what you're on to. You're like, well, what if you got to do it between two expressions? And that's where I'm going with. We're going to have to make a new formula, everyone. This was called the washer method. Washer method would be pretty easy. I mean, the disk method. I'm talking about, let's now look at the washer method. All right, so I'm going to put right here, put a line. What about a washer method? What's this for? Well, I'll go back to here. Remember this image before? Right there? What's a washer look like? Something like this, right? Now, if you were in a geometry class, and you had to get the area of this washer here, do you all agree I could just get the area of the bigger circle, and then subtract out the area of the what? The smaller circle. Wouldn't I get the area of this region? That's the formula we're looking at for the washer method. Okay? So what I'm going to present to you now is see y equals x? I'm going to stick another curve in here. How about, I did x squared before, I'm going to use x cubed. Get this out of the way. You know what x cubed does like a snake? I'm going to get this out of the way. Just erase this. And let's just take a curve. It goes like this. X cubed comes up like this. Then it comes around like this. Eventually it's going to meet that straight line. We're going to find, this is in 6.2. Let's find the volume of the solid that's generated by revolving the region between y equals x. What was my other curve? Y equals x cubed. I do want to point out, didn't I only put this in the first quadrant? So I'm going to make a note of that as well. Everyone, in quadrant 1 only. Because I think a lot of you would agree, we're going to find the volume of the solid generated by revolving the region in that first quadrant about the x-axis. So this thing's now going to get revolved around here. And we can make a pretty decent image, but I'm going to come back to you to find out what the heck we're going to use for those places where they meet. It's still that same method, isn't it? The intersection method. So when you want to make a rough sketch of what's going on here, this is y equal to x. This curve right here is what? Y equals x cubed. First, can we figure out where they met? I only took where they met in the first quadrant. Where did they meet? Somebody just do it in your head. What is x equal x cubed? Nothing tricky. X equal to 1. Does everyone agree? I mean, you could have done 1. X equals x cubed and solve that. But does everyone agree? Can you see it? These two functions here are meeting at 0 and at 1. So we already know the limits of integration. We're going to go from 0 to 1. The only thing is we need a math formula. It's something similar to what we were doing with area before. Like the area between curves, everyone? How can I get the volume of the solid generated by revolving this region about the x-axis? What the heck would it look like? If you want to make an image of this on your paper, everyone, it looks like what? This would come like this. This is what? Come be like this. If it reflected, and then this would just what? Whoop, 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 whoop. Something like this, right? And what would it look like? I can point you to some YouTube sites that looks way better. Okay, I'll direct you to that. I can put those in Canvas as well. Where you can really see the what? The cool looking solid, you can look inside of it. Wouldn't it have like a little hole in there? Does everyone see that? Sounds like there's a gap in there. But we're going to get the volume of this solid. Then we need a formula. But it's something about a washer. What should I do? Pi r squared minus the other pi r squared. True? Will that work?
Yeah.
Remember we were talking about before, you said to find the area of a washer, you just take the area of the outer circle minus the area of the inner circle. So that'll be our math formula. Before it was just pi function squared. We can still just factor the pi out here, right? Because they'll both have pi's. And it'll be the, here, let's just call this the outer f of x squared minus the inner f of x squared. You want to use a different letter and put g? And let's call this one g. There's our math formula. Go from some what? A to some b. Outer and inner. Well, we'll talk about that. Who's the outer, who's the inner? So when I want you to look at this image, see, sometimes you might be going around the y-axis, okay? When I'm talking about the outer, I'm talking about the function that's furthest away from the axis of revolution. I should say that a few times. If you're wondering, what do I mean by outer? Look at your image. Which one of these two was further away from the axis of revolution? That's the one that's going there. The one that's further away, because that would be the outer what? Part of that washer. And all you're doing is summing a bunch of washers. So which one is further away? I heard it. Here's the setup. We're going from 0 to 1, right? Isn't that where they met? 0 to 1. The outer is the x. Who's the inner? The x cubed. Now, what did I forget? This happens on test. Look carefully. You hearing us?
Pi.
This can happen. You get partial, we're talking about partial credit. Look carefully, it happens. We just did area. There were no pi's in those area problems. Here you're doing the volume, and it's pi r squared minus pi r squared. Slap that pi down, right? Hey, Sean, Are you ready? So, what if I had these mixed up? What's the saving method to take care of it? She said, put absolute value bars where? You follow me? Again, we'll call it Sean's theorem, but she's saying, if you accidentally had the what? The outer and the inner mixed up, we're saying to save it, put your absolute value bars where? And you'll get the right answer. You really, with all that math? Yeah. You would discover because you get a negative answer. Hey, can we solve this? What's the integral of x squared? X cubed over 3. Is that x to the 5th or x to the 6th? Help me out. X to the 6th. That's where you multiply, right? What's the integral of x to the 6th? 7 over 7. 0 to 1, put your pi. One thing you gotta help me out is, what is 1/3 minus